Good day and welcome to the webinar on mechanical ventilation control using Flownex, where we will take a closer look into the control of the ventilator and how it was implemented. If you would like to view the webinar on modeling a mechanical ventilator in Flownex, please click the card on your screen. Let us briefly look into the background of Flownex. Flownex is a system design tool that solves the mass, momentum and energy conservation for large thermal fluid systems. Flownex is used in many industries for tasks such as HVAC design, control systems optimization, and many other types of industrial processes. Flownex also contains a large library of control components which can be easily integrated into your existing Flownex flow model. Flownex also contains a library of visualization elements that allow you to build your own custom human-machine interface or HMI. Some of the components that is built in Flownex are the PID component, which enables proportional, integral, and differential control, switches, for example, to compare different inputs, mathematical components, counters to increment values, logic gates such as AND and OR gates, timers, etc. On a side note, Flownex uses a green nomenclature indicating digital links and a red nomenclature for analog links, but more on this later in the webinar. Before we begin, let us jump back to a quick overview on mechanical ventilators. Mechanical ventilators supply oxygenated air to a patient's lungs if the patient is not capable of breathing on his or her own. Of course, the lung is a sensitive and complicated organ. It is therefore vital that the air is firstly supplied within tolerable pressure and volume bounds. Furthermore, it is important that the air be supplied within a time-specific manner as required by the breaths per minute. And finally, that the air be humidified and heated as required. For our control demo, we will specifically be looking at supplying the air within tolerable volume bounds and also within a time-specific manner. Previously, we looked at displaying the ventilator as a pneumatic system, where we have our two tanks for oxygen and air, the two valves controlling the amount of oxygen in the air. We also have the inspiratory valve controlling the flow. We have an air resistance representing the trachea or bronchi. We also have the expiratory valve controlling the breaths per minute, a variable volume representing the lung, and we have a control system controlling the inspiratory and expiratory valve. If the lung is breathing in, then air will flow from our tanks to our variable volume. If the lung is breathing out, then air will flow from our variable volume through the expiratory valve and out to atmosphere. So without further ado, let us look into the control methodology. To implement a control strategy in Flownex, the design engineer can simply ask the following two questions. What do we want to control and how do we want to control it? For our mechanical ventilator, we first want to control the breaths per minute, or the time it takes before the next breath is forced by the ventilator. This is done by opening the expiratory valve. The next control component is PEEP for positive end expiratory pressure, which is the pressure of the lungs in between breathing states. This pressure is controlled through the opening of the expiratory valve. Lastly, we want to control the volume flow, which is controlled by opening and closing the inspiratory valve. This control is also only active when the lung is breathing in. We will now continue to look in detail on how each of these control modes have been implemented in Flownex. We will first take a look at how to implement the breaths per minute. Initially, we need to obtain the current state of the lungs. This is required as the time between breaths should only be calculated once the patient is in rest. We will make use of specific double properties as shown, which is essentially the interface between the flow model and the control model. Following this, we need to activate the time between breaths, where we will use an on-delay timer. This component outputs an on signal after a set time of activation. The control mode that we are implementing is called intermittent mandatory ventilation. This means that the patient must be able to take a breath between breathing cycles. For this, we will make use of a toggle switch to activate if a breath is induced by the patient. We also do not want to change the opening of the valve instantaneously. Therefore, we will make use of a rate limiter. Lastly, we will make use of digital constants to input constant values into our control network and a NOT gate to obtain an inverse of a digital value. So let us jump to Flownex. This is the Flownex simulation environment where at the top we can see our flow model and at the bottom our control model. The control components have already been placed on the canvas where they can be obtained from our distributed control system. Under analog components, there are, for example, the PID components, digital components, and there we can find our timers, for example. For this webinar, we will simply link these components as we go through the control methodology. First of all, we have a specific double property, which is linked to our long script. This can simply be done by selecting the long script and selecting the property that we want. Furthermore, if the lung is breathing in, then the state will be 0. If the lung is breathing out, the state will be 1. Our on-delay timer is activated only by a 1 into the set input. So we need a NOT gate to inverse the input. We will link it as shown, and we'll link the output of our on-delay timer to a toggle switch. The on-delay timer contains, first of all, we added an invert output because when the patient is breathing in, then the expiratory valve must be closed, and if the patient is breathing out, the expiratory valve must be open. The preset time is set by a quick script, which enables us to do some basic calculations as shown. Furthermore, we can now continue to connect our system to the next toggle switch, where I'll explain this component in a later 30-minute webinar. Lastly, we can second last, I can connect my toggle switch to our rate limiter, which enables the valve to open and close, but not instantaneously. We have an increase rate of around 1 per second and a decrease rate of around 10 per second. I can further link the output of our rate limiter to a specific double property linked to the expiratory valve's opening, as shown. Finally, I want to link my lung state also to the reset, as when the lung is breathing in, then our counter should reset. Also, I want to activate a breath by the patient, and we therefore have another input to our toggle switch here, which is done by the digital constant. Remember, if the expiration valve is 0, then it means that flow is going from the tanks to our lung component. This patient breath is linked to a property where if this is set to 1, then it means that a breath is being forced by the patient. We now want to display the results on our canvas, so we can go down to visualizations, graphs, and select a line graph. What we want to display is the opening of the expiratory valve, so we can simply select the component, select the fraction opening, and drag and drop it on the canvas as shown. Now we want to give our graph a title. This is the expiratory valve opening. And we can simply solve and run the network. Now we will see the valve open as the patient finished taking a breath, as shown. And let's pause it there. As we can see, this occurred over 1 second, as set by our rate limiter. Let's continue the simulation. And the patient is currently breathing out. And we can see that currently the expiration state has finished and the valve closed and the patient is breathing in again. Currently the lung is in rest state and the timer is counting as shown. It currently finished. And let me just hover. There we go, the counter is going. So let's stop the network here and let's continue on with our presentation to implement the other modes. The next mode that we want to implement is the positive end expiratory pressure. And for this we will use again the expiratory valve's opening. The first step is of course to obtain the lung's current pressure. To do this, we can make use of the specific double properties. Following this, we want to control the PEEP. For this, we can use the PID component, which will sense a value and control the output based on a set value. Furthermore, we also want to activate PEEP control only whilst the lung is in rest state. To do this, we will make use of a toggle switch to switch to PEEP control only when rest mode is active. Lastly, we will again use the rate limiter to not instantly change the opening of the valve. So let us jump to Flownex. First of all, we've got a specific double property for the pressure of the lung and the specific double property for the PEEP. Let's zoom in a bit. And we want to connect the pressure to our process value in the PID, the PEEP to our set point, and also we want the PID only to be active when the lung is in rest state, or in this case breathing out. And also let's link the output of our PID to our toggle switch over here. Also the PID, if I zoom into the PID a bit, it contains various variables. For example, the present value, the set point, the manual value. In this case, we're controlling a valve, so the output high limit should be 1 and the low limit should be 0, and different proportional, integral, and differential gain values. Also, we have the mode, where if it's in auto, it will be 1, which is set by our current lung state, as you can see here. If I zoom into this, you can see all the inputs to our PID component. Finally, let's link the toggle switch as shown. And let's view the results. Now, before we start, what will happen, let's just run the simulation, is that the valve will, let's continue with the simulation a little bit. So what will happen is that when the patient is breathing out, the valve will open, but then it will start closing again as to obtain a specific PEEP. It will stay at that specific value for a moment, and as soon as that PEEP has been reached, then the valve will close again and the lung will be in rest state before the next breath will occur. Let's just wait for the patient to breathe in, and in this case it breathed in and the breathing out cycle work started, and the PID is currently controlling the expiratory valves opening to obtain a specific PEEP value. And let's pause the simulation there. Furthermore, as indicated in the beginning, that the green lines indicate digital variables and the red lines indicate analog variables. If the line is dotted as shown, it means that an analog component is transferring a value to a digital input as shown. But Flownex will not have a problem with this as long as the input for the analog component is either a 0 or a 1. Let us jump back to our presentation. The last step in the control implementation is to implement volume control. The volume flow is controlled by opening and closing the inspiratory flow valve. The first step is to obtain the current flow. This is done by again using specific double properties. After this, the required flow needs to be set, which can be done by using an analog constant. A PID component can again be used to open the valve to obtain the required flow. And also, it is vital that the flow is only active when the lung is breathing out. A comparator is therefore used to check the current state of the lungs. Let us finally jump back to Flownex. So here we have our flow control. And the first step that we need to do is we need to link the current flow to our present value in our PID. After this, we've got a constant that specifies the current flow conditions, and we can link it to the set point. It is important to note that Flownex works in base SI units in the control system. Currently this is set to 30 liters per minute, but the PID will work in cubic meters per second. So we can simply add again by changing the unit from liters per minute to cubic meters per second. Also, we only want the flow control to be active when the lung is breathing in. To do this, we have a comparator, which basically checks if the flow is positive. In this case, I have the flow connected to input 1, and I have a constant set to 2 connected to input 2. In this case, since there is some variation in the flow that can occur in the network, I did not make the 0 but 2 in this case, just for stability. I can link it as shown, and I must remember to ensure that the conversion from liters per minute occurs to cubic meters per second. Finally, I must link the output of this comparator to my auto manual value of the PID. I also want to set a manual value for the PID, so I can link it as shown. Finally, I can link the output of my PID to my input of my rate limiter as explained earlier, and I can link the output of my rate limiter to the inspiratory valve. What I want to do now is I want to graph the results. I'll again use a line graph, and in this case I want to plot the inspiratory valve's opening and I want to plot the current flow of the lung. Furthermore, I want to add a title to this graph. Let's call it the inspiratory valve opening, and let's display these results on different axes. I can simply solve the network and we can run the network. As we can see that currently the total volume flow is set to 30 liters per minute, and we can see the blue line indicates the valve opening as it tries to control that total volume flow during a breathing in cycle at around 30 liters per minute. Currently the lung is in rest state and it will breathe in again, where the flow valve will try to control that to around 30 liters per minute. Let's stop the network for there. We also have an HMI built as shown in the previous webinar, where for example we can increase the breaths per minute to, let's say, 6. And what we'll see now is that the breaths will occur much more frequently. Let us pause the network there. To summarize, Flownex contains an advanced control library, which can be easily coupled with your Flownex flow model. The user can effortlessly display the results from the control system using the built-in visualizations. Also, there are a few video links which will pop up on your screen momentarily that might be of interest, such as PID controller tuning, co-simulation with Flownex and LabVIEW, and also modeling transients in Flownex. Thank you again for taking the time to watch the webinar. Please feel free to reach out to us through inquire@flownex.com, where we will be in contact with you. Also visit our website for more information on Flownex and how it can be of value to you.